So welcome back. Now we are going to move on to a practical part. So that's the good news, right? You concentrated a lot last week with the theory and the heavy math. Now we are going to be looking at practical things, how to actually use SQL, and you can even do it in the notebooks on your laptops. You'll do it in the exercises. This is very pleasant because this is a cool thing with computer science is that you see what you do, right? You just interact with the machine. You can play with it. You can test it. You can try to make it crash. You can, experiment and see what happens. So this is very pleasant to do. But let me repeat once more. So now we know what data looks like. We know what a relation is, right? If you take two sets, a relation is just a graph, really, that links every element from the left to, that links some elements to the left with some elements to the right. But it's fully general. You can associate elements to 0, 1, 2, as many as you want. So it's very generic. Then if you add a constraint that you associate the elements on the left with at most 1, so 0 or 1 elements on the right, then you get maps. And if you require furthermore that it's exactly 1 for all of them, then you get a function, right? So relation, map, function. There was even a discussion because people ask injective, surjective, bijective. I answered because it's interesting and it's nice you're curious about this, but this is not central to the databases, right? But it's interesting, This is what I like about this kind of lectures is that even though we focus on databases, it's a good rehearsal of sets and logics, and that can actually be useful in many other courses or many other lectures or even later. So it's not a bad thing to cover this. All right, so we have this. Then we have the set semantics that we have sets of records. But if you just say set of records, then you could have this which doesn't glue together as a table. So this is why you throw in these 3 rules, so relational integrity, domain integrity, atomic integrity. And the intersection of the 3 rules gives you SQL. So if you have a set of maps with these 3 values, that's a relational table, or a bag, or a list. Okay, so now that I've repeated that for the millionth time, let me now dive into SQL, so the practical parts. So even though relational tables are thousands of years old, things really started to accelerate in the 1970s. So after Edgar Code came up with the idea of data independence, people started thinking about how you implement data independence. How do you make it possible for people to only care about tables without worrying on the implementation? And what you need is a language. So not a human language, but a computer language, programming language. And so these people, Don Chamberlain and Raymond Boyce, they came up with a language that they called SQL, as in Structured English Query Language. So the name indicates that it should be natural and sound a bit like English. So of course, it wasn't ChatGPT yet, but it was kind of the idea that it should be natural, right? So it's these 2 people. Don Chamberlain, by the way, was involved later in X-Query and basically breaking these rules, right? So what we do when we start breaking these rules in big data for engineers, Don Chamberlain was involved in doing that as well. Okay, so it all happened in the 1970s in California, in San Jose. Who has been to California or over there? Okay, some of you. So San Jose is a little bit in the southeast of the Bay Area. Near San Francisco. If you want to go to that laboratory, it still exists today. You just need to go a little bit in a desert, almost a desert area for a while, and then you arrive to the laboratory. It's known as Almaden today. So they came up, IBM, with the first commercial relational database that they started selling to customers. They called it System R, and they had this SQL language, as I said, Structured English Query Language. That's what it meant. And the first customer was Pratt & Whitney, which was 7 years later, right? So data independence 1970, and the first customer who paid for these systems 1977. So the idea of the language of SQL was that first it should be declarative. You might remember 2 weeks ago what I told you about. Declarative means like you go to the Mensa and you ask for the menu you want, as opposed to cooking yourself, which is called imperative, right? So imperative would be like Python, Java, C++. They're a bit more complicated, but SQL is declarative. You just write down what you want in the notebook. You just say, this is what I want. Give me the data that looks like this. So SQL is declarative. That makes it actually quite easy to learn in comparison to Python or other languages, right? Furthermore, it is set-based. Set-based basically means that with just a few lines of SQL, typically 3 lines is the standard queries are on 3 lines, you can manipulate millions of records. You can manipulate a table that has millions or even billions of records. And that feels actually very powerful, right? Then you get these people I remember at Google that had stickers like, my computer is a data center, right? Because you can just write a few lines and then suddenly you have massive amounts of data. So it's called set-based. It's different from Python or C++ or Java because in these languages, Python, C++, Java, you manipulate one thing at a time. One thing at a time, right? Every function returns one thing that can be an object, can have some structure, but it's always one thing at a time. But with SQL, it's very powerful because again, you can manipulate millions or billions of values at the same time, and that feels very, very powerful. So we call that set-based. And again, set-based is to put in perspective with set of maps, right? So this is how it's called, okay? Now, as you know, we changed the SQL to SQL because of a trademark issue, and this is why many people say SQL, many people say SQL. I tend to say SQL, so maybe at the end of this course, you will also tend to say SQL as well as a consequence. But anyway, it doesn't matter. You can just pronounce it either way. It's exactly the same thing, SQL or SQL. All right, so now let's dive into it. So we have this schema here, and this is the one thing we want to implement in SQL. So what I will now spend a bit of time on is these domains here. Integer, string, and so on. I'll equip you with a bit of theory of what kind of domains we can have. Then I will tell you how they are called in SQL, and then we'll use the names, however they are called, to create table statements in SQL. So the kind of domains we have here, there's just integer and strings, but we have a lot. We can have strings, we can have Booleans, so yes, no domains, we can have numbers, dates, times, very important, often neglected by software systems, but companies really need them. Enumerations, binary, pictures, for example, you can put pictures in a table too, durations, and so on. There is a SQL standard that gives the domains, but just as a word of warning, the implementations do not exactly use the same names. So if you look at PostgreSQL, IBM, Microsoft SQL Server, Oracle, they don't use exactly the same name. But it's okay. I mean, once you've learned what they look like, you just learn the new names when you use a new system, right? You look at the documentation. All right. It's a bit like Zürich-Deutsch, Basel-Deutsch, Schweizerdeutsch, Welschdeutsch, if you want. So you just, everybody understands each other. So let's start with strings. So it's something for computer scientists that is very natural, but if you're not a computer scientist, that might not be that obvious, right? So what is a string and what is it called? Why is it called a string? It's basically the idea that it's text. But if you look at text, what it's really is a sequence of letters, a sequence of characters, right? So this is what you get if you look at this. So the quotes are not part of it. We like to put them in quotes. You've probably seen that in Python or other languages, but the quotes are not part of the strings. So for example, the first one, foo, is really made of 3 letters, F-O-O, then Zurich, then Ilsebill, that's the Nacht, that's from famous literature. Yeah. So this is a string. So now, what can you do with strings? Well, you can say, for example, that in your table, you want to have the car registration plates, and you want to specially ask for Swiss content. So maybe you want to say that your string has exactly 2 characters, 2 letters, right? And that you can do. That's a fixed length string. The second thing you can do is to have some limits, but still variable. And that's typically with country codes, for example. If you want the country code of the car, some countries have just 1 letter, like France, F, Germany, D for Deutschland, Italy, I, but some countries have 2. Great Britain, so GB for the United Kingdom, CH for Switzerland, some have 3. These are standard codes. But here it's not like the contents. Here you have a variable number. you can also do that. For example, you can say, I want a string with at most 3 letters, at most 3 characters, okay? And finally, you can also say variable length without any limit, any text, right? Imagine that you have a database that has blog entries, right? Who has a blog here? Whoever used WordPress, right? So WordPress is an example of blog that actually has a relational database behind. All of what you write in WordPress is eventually stored like this in the in that kind of type. So you can say variable length without limit, meaning that people can be creative and write blog posts as long as they want, or you can set a limit and so on. All right. Now, for every type, I'm going to tell you what they are named. So there's actually many synonyms, so do not be too much confused. It's just really synonyms that mean the same thing. So for fixed length, you can just say char 10 or character 10. It's the same thing, and 10 specifies the number of characters, right? So you can change it, of course. You can put any number you want in there. Then you have, if you want to make it variable, but with a limit, you can say character varying or varchar, which is just an abbreviation. If you're too lazy to write it completely, just write varchar, and then the number in there, right? And then if you don't want any limit, you can just call it text or varchar without anything here, or club. Club, it's all very funny. It means character large object, right? That really just means text, but it means there's no limit on the size that it can have, right? So now, if you look closer, let's say we did in SQL define and create a table that has these types as columns. So here I used char 3, so this is fixed length. Here I used varchar 5, so it means up to 5 characters. And here I put just text, which is unlimited, right? So the third kind. And I created 3 columns. Then imagine that I'm trying to insert in every column, I'm trying to insert these values just so that you see what it means. So first, let me take this one, the F. So if you put it in the variable length, it's just going to store F. The same if it's unlimited, so it just stores that one letter, right? Here it's less than 5. 1 is less than 5, so that's fine. But look at what happens here with the fixed length. It has F, but fixed length means it has to be exactly 3. So what it's going to do is add 2 spaces here, F space space. So this is just a warning to again say this here really eats the entire space. If you say 10 characters and you have less, you're still going to have spaces. So this really has a very predictable number of letters in there, right? If it's varying, that's a bit more memory efficient, because if it's less, then it's really going to use less memory, right? So this is good if it varies to use that one. Then, of course, if you just put nothing, then you're going to get 3 spaces here, and here is going to be empty. Here, foo is going to work for all of them, right? Here is exactly 3, so that's good. Here it's less than 5, and here we can put anything. Foo bar is going to be rejected here. You will get an error. That's a very nice feature of PostgreSQL and search systems. They will throw an error and not let you do it, right? So here you get an error because six letters here is more than 3. Here it's also more than 5, so you get an error as well. And here you don't get any error because that's any number of letters. So here you can just put it in there, right? And if you put foo with extra spaces, then it's going to truncate the spaces. So here is going to just keep 1. Here is going to truncate to 5. And here it's not going to truncate anything. For whom does that make sense? Right? So you have 3 main kinds of types for strings. You have fixed length, variable length with or without limits. Okay. All right. Now, in general, if you don't know which one to take, many people go for varchar. Even for text, they would take varchar 255 typically. You have a question? You can. No, I think it's 1. If you just say char, that's the length of 1. That's something we can check in the documentation, but I think this is what it means. Char is just 1 character, and then if you want to specify more, it's going to be 10. Okay, thank you for asking. By the way, I put this non-standard here. What it means is that this is in PostgreSQL, but if you look at the SQL standards, then you won't see it. It would be called club in the SQL standards, right? What's very sad is that you need to pay for the SQL standard. So I don't really like that. I don't know why they put it behind a paywall. It's not the case of all standards. But what you should look at for the purpose of this course is the PostgreSQL documentation, right? Where they explain everything. You will also have that at the exam. You'll have access to the documentation. I will show you the pages that you can look at. All right? So yeah, these are all synonyms. All right. And again, this is when I said that if you use a different system than PostgreSQL, like IBM or something else, then test might not work, then just try varchar or try club or look at the documentation. And again, if you use char, be careful because that's going to eat up all the space. Even if you don't use the entire n letters, it's going to add spaces. So this takes a lot of space. Be careful with that one. Okay, that's the strings. Now let's turn to math. Let's turn to integers. So technically, an integer is something that is whole, right? It doesn't have any decimal parts. We started, I mean, when humankind designed that, we started with the natural integers when you count stuff. So 1, 2, 3, and so on. Then 0 was invented, and then negative numbers were invented, like negative temperatures. Mathematicians call it Z, right? So mathematicians call it a ring with addition and multiplication, but that we don't get too much into details with that. But the idea of integers, now if I look at integers from a database perspective, then I have to be rigorous about what I'm doing. When I talk about integers, I'm really talking about the idea of an integer, right? If I say 2, that's the idea of the number 2, right? Can be 2 apples, it can be 2 tables, right? It can be 2 of anything. This is a mathematical idea, right? If you think of Plato, that's a bit this kind of philosophy. So an integer is really something abstract in our minds. Now, when you use a computer, you have to encode that thing, that abstract. And of course, even before computers, what we started doing, our ancestors, is they wrote them down using digits, right? It used to be, for example, in base 20, I think in South America. We adopted base 10 at some points. But again, depending on the civilization, it can change. In fact, we also use base 60 for the hours and the minutes. This is in fact in base 60. So this is an example. And that in fact changes how you encode it as text. Because in the end, when you encode an integer, it ends up as text. So for example, if you want the concept of oneness, right? The mathematical number 1, then you can write it down as the digit, the decimal digit 1, or 0, 1 is the same thing. You can put a 0 in front of the 1, that's still the oneness. There is a name for this when you actually encode as a string. So it means you literally type on your keyboard to do that. This is called a lexical value or a literal. These are the two names, a literal or a lexical value. And when you have a type like the set of all integers, you in fact look at it from two perspectives. You have the value space that is really Z, that's the value space of all integers, but highly abstract. Then you have the lexical space. What is the lexical space? It's the set of all strings that can be understood as a number, right? So 102 is a string that is in the lexical space of integer because you can parse it as 102, as the number 102. So technically, the lexical space is made of anything that can be decoded as a number, right? So for example, 4 can be 404. You even have, and computer scientists can also put it in base 2, right? So 100 would be 4 in base 2. Base 2 is something that computer scientists do a lot. Most people are used to base 10, even though not every primary school do that. But normally in primary school, some teachers teach you other bases to count, right? In base 10 means 1, 2, 3, all the way to 9, and then 1, 0. But who learned to count in other bases in primary school than 10? Not many of you? Okay, who heard that you can do it in other bases? Okay, so that you know, right? So base 2 is the one computer scientists love. It's basically a 0, then 1, and then 2 doesn't exist in base 2, right? So then it's 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, and 1, 0, 0, 0, 0. So this is how it works. And what computer scientists can do is they can want to write this 4 in base 2, then they write 1, 0, 0, and the B just means binary, right? It just means that it's in base 2. So this is the sort of thing you can have in computer languages. They also have special codes for base 16, which they like to use. We have a code for base 60. That's the colon. When you write down a time with hours, minutes, seconds. For example, 1 hour, 30 minutes, you write 1 colon 30, right? That is also a lexical space, right? That would be 4 times, but this is the idea, all right? So again, the important thing is there in here, what I'm telling you is that there is on the left, the mathematical abstract view of the domain. This is what is in our minds. And then there's the actual text that you're going to type on your keyboard when you want to actually create the values in Jupyter Notebook, and that's called the lexical space. Okay. Now, typically in many programming languages, the set of integers are restricted. It's restricted in the number of bits that you use in base 2. For example, bytes in Java. Who uses Java? Some of you? Nobody uses Java? Some of you, okay. So in Java, we have 4 kinds of integers. We have byte, short, int, and long, and they really depend on the number of bits that you're using. So int used to be the common one with 32 bits. It basically can cover, if you count how many numbers that is, imagine that basically goes between 32 zeros, and then you count in base 2 all the way to 32 ones. And 32 1 is basically 2 to the power of 32 minus 1. And 2 to the power of 32 is very roughly 4 billion, right? 4 billion. So it means that int, for example, with 32 bits, can encode number between 0 and roughly 4 billion. This is what it does. Short, 16 bits, that would be, I think, all the way between 0 and 65,000, very roughly. Bytes 2 to the power of 8, that would be all the way to 255, between 0 and 255. This is more limited. In fact, on YouTube, you watch videos, right? On YouTube, the counter of the number of views used to be an int in the early days. It would go all the way from to a few billions of views. And you know the video that broke that? Who remembers Gangnam Style? It broke the counter. That actually broke the whole counter, and it sent it back to 0, basically, right? So they had to change the counter, and this is because of that video that they had to change and re-implement YouTube to change the counter to a long with 64 bits. And 64 bits bring you to 16 quintillion. So I think we'll need some time to reach 16 quintillion views on a video on YouTube, right? Okay. So yeah, these are the common types that you have in systems. Nowadays, if you don't know, people tend to use 64 bits because that's the new computer architecture these days is based on 64 bits, right? I wrote it down for you, by the way. 16, that's that's the interval. What I'm showing here is called the sign integer. If you want to allow for negative integers, then you basically the convention is that if the first bit is a 1, that's considered negative. If the first bit is a 0, that's considered positive. But then you lose 1 bit to encode the number. So this is why when I told you it's up to 4 billion, well, if you use one of the 32 bits for the sign, then that's for minus 2 billion to 2 billion, right? For whom is that clear? Right, because 1 bit is for the sign. Okay, and here's your almost 16 quintillion. That's even 18 quintillions, I mean, because the powers of 2 tend to grow a little bit faster than the powers of 10. Okay, so these are the integers. And these are how they are called. So if you want one of these 64-bit integers, it's called big int in PostgreSQL. So very easy to remember. Then you have just int or integer that would be the 32 bits one that is kind of losing losing its appeal now, but some people still use it. And then small int is on 16 bits. Okay, so small int, big int. This is how they are called. Okay, and again, the idea is that you write it in base 2. So these are just a few examples. What you see here on the screen, 0, 2, 5, 11 are the lexical values in base 10 of the numbers 0, 2, 5, and 11. And on the right, you have the lexical value in base 2 of these same integers, right? But always have in mind that once you store it in a database, it's really the number 2, the number 5, the number 11 as mathematical objects that you're manipulating. Okay. And then came the decimal dots. When you start dividing your pizzas, and this is also something that, that people learn in primary school. How do we store that? It's actually much more complex than it seems to store. So one of the approaches is to just forget about the dot, store it as an integer. For example, you can just, you just store it like this as an integer on 32 digits. And then you remember where the dot is somewhere else. For example, you could create a column and you say for that column, I'm accepting 32 bits and the point is always there. I'm just not putting it explicitly in the values that I store in my machine. I just assume the dot is always here, right? The decimal period. And so this is one way of storing decimals. It's called the fixed point decimal storage. It means for one column, the point is always at the same place. So when you do that sort of things, you need to tell the database system how many digits you have in total. That's in base 10 in that case. How many digits in base 10 do you want to be able to store? That's called the precision, right? That's actually extremely precise. I mean, if you give that to a physicist, they will tell you it's totally useless to have that much precision, right? But this is just to give you an example, right? You can also have a precision of 2, of 10, of whatever you want. So the total number of significant digits is the precision, and everything beyond the precision will just be dropped and forgotten if you go beyond that. Then you have what's called the scale. The scale is what I mean with the position of the period. It basically tells you you have 22 digits, then the decimal period is here, then you have 10 digits right here. This is called the scale. So now if you want to create a column in a database management system that works like this, you need to tell the precision and the scale, right, of your type. And that's it. And then it's going to store it. Now, you can also say, I don't care about any precision and any scale. It's going to be more resource consuming. That's called numeric or decimal. You can use any of the two. That will allow for any decimal number that has a finite representation in base 10. That's numeric or decimal. If you want now to specify a precision, like for an integer, but scale of 0 means you don't have any digits after the decimal period, then here you say numeric 32. It means an integer with 32 digits and a scale of 0. And then you can limit the precision and scale. Then you just specify 2 parameters. You first have your digits and your precision, and then you have your scale, right? So 3222 would be this here. 3222 would be storing that kind of numbers, okay? And then you just put it in parentheses, right? Behind numeric or decimal. It's just like with char, right? If you just say char, it's 1. And then if you specify an addition, that's going to limit it. Varchar is the same. So varchar would be unlimited, and varchar together with the number inside is the number of letters. Here it's the same thing, but with the number of digits in the base 10. For whom does that make sense? Right? And what you see on the right, numeric, decimal, and so on, you can actually literally write it down in your Jupyter notebook to create columns with that type. So that we will do in the exercises. So now concretely, what's going to happen if you create columns like that and try to insert numbers? So we'll see that if you have 0, will be 0. A number, if you have useless digits, you know that if you have zeros on the left, that's totally useless. You know that the zeros mean nothing, so they are going to be taken away. 3.1 and plenty of useless zeros here, that's just removing the zeros. If you have here a scale of 0, if you don't put anything, it's a scale of 0, meaning no decimal after the comma, that's just going to round, right? So it's taken the 1 away. And then if you allow for 1 decimal after the comma, so precision of 3 and 1 decimal after the comma, then 3.1 is fine. 3.14 is fine. Here it's truncated, rounded. And here it's rounded again because there's only 1 decimal after the comma and there was 2, right? So you just remove it. Then what if you try this? The numeric accepts anything, right? So any precision, so that's fine. And here, precision of 3, but here you have 4 digits before the comma. So you cannot do anything with that, right? You could try to truncate it all the way here, but then there's 4 digits. That's too much. So that's going to be an error. And here it's also an error because it says precision of 3. So that would be too much. For whom is that clear? Yes?
Say truncated, sometimes they rounded.
Rounded, truncated is when for the strings. I said truncated.
3.16 numeric, the last one would be 3.1 or 3.2?
I think it's 3.2. It's rounded to the nearest. So 3.16 means 3.2. But be careful, because for the negative numbers, you have the choice between near to the nearest or to away from zero, what's called away from zero. And there's also a different convention that is used by accountants somewhere, is that you round if it's a tie, 0.5, it's rounding to the even number. So this is what accountants do in order to, I don't know, they spread the distribution somehow, but basically 3.15 is rounded to 3.2 and 3.25 is also rounded to 3.2, right? But these are really implementation details, right? These sort of things. And you have to be careful because the conventions might not even be the same for these types than for other types. But here we're really beyond what I expect you to remember, right? So just remember it's rounded, and the details of how it's rounded, I'm not going to, ask that at the exam, the details of that. Just we round, that's basically it. Does it answer your question? Yeah, all right. So let's take a break, and then I'll continue driving you through the types, then showing you some SQL queries.